Hi all. In earlier videos, we have learnt about this method called logistic regression, which is one of the most popular and most powerful methods in supervised machine learning. So although its name has the term regression, but essentially it's an algorithm for classification. So this diagram over here shows a simple example of binary classification where you have these crosses colored blue and you have these crosses colored green, which have to be separated from each other using the input features xi. So for some values of the features xi below a certain threshold, the output yi is equal to 0, representing one class of the binary classification, and for xi values above a certain threshold, the yi values are 1. Of course, there are some cases of points which actually lie on the other side, but these are inevitable in any real life data set. So here what we do is that we find a linear decision boundary represented by this straight line in this case, and we fit a logit function denoted by this h, which gives us the probability of a certain output class given certain input features. So these theta values are the model parameters which have to be learned using a process of gradient descent. So now, although this is a very powerful method and very commonly used, one severe problem with logistic regression is that it is very bad at handling outliers. So let's say, for example, you have a lot of points over here, but suppose one data point, or let's say a few data points, were quite away from the majority lot. So the majority lot is over here, but there are these outliers which have a very large value for the input feature. Now what will your logistic regression learning algorithm do? It will completely distort your logit function, and now the new logit function which you map to the data will look something like this. So now this is distorted because of these extra data points, and now some data points which were actually in the yi equal to 1 category may now be categorized in the yi equal to 0 category, leading to large errors. So this is the problem of outliers, which logistic regression is very bad at. Okay, so now how do we address this problem? As they say, if you want to get one thing, you have to give up something. It's always a barter system. So if you want to be able to handle outliers, you have to give up something that your logistic regression helps you with. And that is this estimate of probability. So as I said, in logistic regression, there are two things that you do. First is you find a decision boundary, and then you fit a logit function so that you can estimate these probabilities. So in SVM, what we do is that we keep our decision boundaries, but we give up on the probability estimate. What that means is that we no longer have to worry about fitting a logit or another function like this, and all that we care about it is finding these decision boundaries. And intuitively you can see that no matter how many points I add as outliers over here, my decision boundary does not get affected because I am not trying to fit a logit function. All that I am trying to do is to find a boundary which separates my class 0 from class 1, and so outliers do not affect that function because I am not trying to estimate any probabilities. So how would that change in the 2D case, for example? So this, you see one feature xi1 and another feature xi2, and these are the points. Let's say for this point your yi is equal to 1, and let's say for these points your yi is equal to 0. So in the logistic regression case, what we had is that we had this decision boundary, and if this function was greater than 0 for a particular input vector, then your probability estimate was larger than 0.5, and if this number was below 0, then your probability estimate was less than 0.5, meaning that your input feature vector now is classified in class 0. So in SVM, what we do is that we get away with these probability estimates. So we no longer have probability estimates, and all that we say is that this implies that your yi prediction is equal to 1, and this implies that yi prediction is equal to 0. Okay, so now we have lost a major power of logistic regression, which was to estimate the probabilities. So in SVM, the algorithm will not tell you how good the prediction is, that whether you are in class 1 with 100% probability or in class 1 with 50% probability. That we totally give up in SVM, and all that we know is whether we are in class 1 or 0. So although that does seem like a major loss, but in many applications which especially have outliers, this can be a major boon. And because we have given up on our probability estimates, SVM turns out to be much faster than logistic regression. So if you want speed and if you have outliers, then SVM is the preferred choice as compared to logistic regression. SVM also has a major advantage, especially for data sets which are not linearly separable. So here we saw that your data points are into two classes, and the classes are linearly separable, meaning you can draw a straight line which clearly separates the class 0 from class 1. But there are many problems where this simple linear separation does not work. Now in logistic regression, it is possible to do nonlinear decision boundaries by essentially transforming variables. So now let's say you have certain data points which look like this, that you have these data points over here which are in class 0, and the class 1 data points are surrounding the class 0 data points. So now obviously in this case a linear decision boundary is not going to work, because clearly you can see that the decision boundary is actually some kind of a circle. So now in logistic regression also you can handle this kind of problem by using variable transformation. So for example, you could say that let's say find the center of this point. Let's say the center is here, which is some vector which is your, let's say, r0 vector. And what you could say is that I have a new parameter r which is equal to the distance of the points from this center. So what you will have is that you will have r vector minus r0 vector norm. So this could be your another variable, and your phi will simply be, let's say, your angle of the r vector. So now using this transformed coordinates, you can still use linear separation, because now in this transformed coordinates your points will look something like this. So what we will find is that the green points will be having a lower value of r, and the blue points will be having a higher value of r, which is evident from our graph. So one could draw this, again, linear decision boundary, and still solve this problem using logistic regression. However, there are many problems in real life where such a simple thing doesn't work, and we don't even know often what kind of transformation may be required. For example, the dataset that you see on your screen right now is somewhat complicated, and it is a priori impossible to know what kind of coordinate transformation would bring you into a space where logistic regression can be used. And that is where the power of SVM comes in, because SVM can handle such nonlinear decision boundaries even when you do not know what transformation function to use. So these details we will see in the next video, but in this video we are going to focus on the linear case where the data points are linearly separable either as raw data set or after doing some transformation of variables. Okay, so now let's see how this SVM method actually works. So as I said, this is very useful when we have outliers. So let's put some outliers over here which would otherwise screw up your predictions for the case of logistic regression. Okay, so what do we do over here in the case of SVM? So in SVM, what we do is that we want to find this linear decision boundary so that it separates these points in such a manner that the separation of the nearest points from this boundary is maximized, and we do not really worry about what these outliers are or how far they are. So essentially we want to form a margin like this, on the other side as well, which is equidistant from our separation boundary. So let's say there is a point over here also, and this point is actually on the margin. So now what we want to do is that we want to find a linear decision boundary so that the separation of the closest points from this boundary is maximized. So separation meaning the perpendicular distance between this decision boundary and the points which are nearest to the decision boundary on either side. So this gap between the nearest point and the decision boundary is denoted by capital M, and our job is to find a decision boundary which maximizes this capital M. So now in order to understand the details, let us magnify over here and then see what happens. So here we have our xi1 and this is our xi2. So we are working for the case of two features, but this can be generalized to any number of features. But as you go to higher number of features, you come across this problem of curse of dimensionality, which is actually a serious problem even with SVM. But in principle, the method is still valid. So now let's say you have a decision boundary, which is, let's say, like this. And you have the margins, which are here. I'm just magnifying so that understanding becomes easier. And on the other side also, at almost the same distance from the decision boundary, and you have these points which are lying over here. Okay, so now these are yi is equal to +1 and these are yi is equal to -1. So here we use -1 instead of 0 for reasons which will become clear very soon. So now let us connect our origin with this point, which is the point which is on the margin. So this is some xi vector. And now for this decision boundary, let us also draw a perpendicular from the origin. So this represents our theta vector, which is the vector of model parameters which we want to learn. And let us also drop a perpendicular from the point to the decision boundary. And let us also connect that point from the origin. So this vector we are denoting as xi perpendicular vector. So this xi perpendicular vector is nothing but the point which is the perpendicular projection from our point which is closest to the decision boundary on one side of the boundary. And let this distance be equal to ri. So now in order to make progress, let us try to represent our xi vector in terms of ri's, theta and the label yi. So now we can write our xi vector is equal to xi perpendicular vector plus this other vector. So xi vector, this one is equal to this xi perpendicular vector plus this vector. So now the magnitude of this vector is Ri, its direction is along theta, and whether you have to add the vector or subtract the vector depends on which side of the decision boundary you are on. So we can write this xi vector as xi perpendicular vector plus Ri into yi into theta vector divided by theta vector norm. How is this working? So the direction of this vector is same as our theta vector. So theta vector by theta vector norm is the unit vector in this direction. So now we multiply Ri with the unit vector to get this. But now we also now have to see whether this vector is on this side of the decision boundary or on this side of the decision boundary. So that plus 1 and minus 1 is taken care of by this variable yi. So now this is a representation of xi in terms of xi perpendicular and these other parameters. Why we are writing it in this form will be clear to you in a short while. So now our hypothesis function h, which is a function of xi and theta. So if I'm not writing the vector notation above, don't mistake, they are the same things. Without vector notation you can always take a transpose and multiply. With vector notation you take a dot product, but finally you get the exact same result. So this is equal to theta 0 plus theta vector plus dot xi vector, which is equal to theta 0 plus theta vector dot xi perpendicular vector plus Ri yi theta vector by theta vector norm. Now see, our hypothesis function was designed so that for points lying on this side of the decision boundary, this hypothesis function would be positive. So this is our hypothesis function. And for points lying on this side of the decision boundary, the hypothesis function would be negative. So what does that mean? For points which lie on the decision boundary, this hypothesis function would exactly be equal to 0. So here, when Ri is 0, the hypothesis function must be 0 and xi perpendicular lies exactly on the decision boundary. So what does that mean? That means that this particular term over here must be equal to 0. So now this theta vector dot with this theta vector is norm theta whole square. You have a norm of theta over here, so these two cancel, and what remains on top is the norm of theta. So the hypothesis function becomes Ri into yi into norm of theta vector. Great. So now what is our objective? Our objective is to find a decision boundary so that it maximizes the distance of the closest points on either side of the boundary. And this is how we avoid worrying about if there are any outliers far away from the decision boundary. So essentially what we are trying to maximize is our value Ri. So basically what we need to do is that we want to find xi for which Ri is minimum. So among all values of Ri, find that xi for which Ri is minimum and then find the model parameters theta 0 and theta for which this Ri is maximized, because that represents the distance. So once again, so this minimization is to find the point which is closest to the decision boundary, And then this maximization is to make it as far away as possible from the decision boundary. So now we have just seen that our Ri is equal to Hi divided by Yi times norm of the theta vector. We can now multiply the numerator and denominator by Yi, and we know that Yi square is equal to 1 because Yi is either 1 or minus 1, in which case Yi square is 1, so this just goes away. So essentially what we want to work with is this quantity, and if we expand this quantity, what we have is that this is equal to Yi into theta 0 plus theta transpose xi divided by norm of theta. So now as you can see, if we scale our model parameters theta and theta 0 by the same scalar quantity, it would make no difference to this ratio, because if we multiply the numerator by beta and the denominator by beta, that would just cancel out. So what we do is that we scale our theta 0 and theta so that yi times theta 0 plus theta prime xi is equal to 1 for the point on the margin. In that case, our SVM problem is essentially about maximization over theta naught comma theta of 1 by norm of theta vector. Because now this quantity has been put 1 for the point which is closest to the margin, so then this minimization is taken care of, because we are saying that whichever point is the closest, for that this value is equal to 1. So now essentially we are left with this maximization. However, remember that this maximization is not alone. We have to ensure that this quantity is now greater than 1 for every single point, because if this is equal to 1 for the point which is closest, for every other point this has to be larger than that, because the distance of every other point is larger than the distance for the closest point. So you need to maximize this such that your yi times theta naught plus theta transpose xi is greater than equal to 1 for all I. So this is a constraint optimization problem, and now instead of maximizing 1 by norm of theta, we can minimize the norm of theta. So we just take a reverse or an inverse or a reciprocal of this quantity, and then instead of maximization we do minimization. And one more change we make is that instead of working with the norm, we work with the square of the norm, because that is easier to implement in programming. So now our SVM problem is essentially about minimization over theta naught and theta of this quantity square such that yi times theta naught plus theta transpose xi is greater than equal to 1 for all I. So this essentially becomes a quadratic program with n linear constraints. So there are many methods of implementing this, and we are going to see one simplification of how to actually solve it. So one more thing that you must notice over here is that we are minimizing this square norm of theta, and this is essentially the term that we used for regularization. So when we spoke of ridge regularization in linear regression as well as logistic regression, we added a lambda times norm square of theta for our cost function. And here this is what we are minimizing. So SVM makes sure that the model parameters are small, and this naturally leads to a kind of regularization. So now in order to solve this problem, so this is a constrained optimization problem, and this is solved using the method of Lagrange multipliers. So what we do is that you define a Lagrange function. So you define this function LD is equal to half of non theta whole square minus summation I is equal to 1 to capital N some quantity alpha I times yi into theta naught plus theta transpose xi minus 1. So these alpha i's are called Lagrange multipliers. So now our objective is to find theta and theta naught so that this LD is minimized, and then we will find alpha I so that our LD is maximized. And why do we do that? Because now assume that all the points that we have satisfy this constraint. So all the points in our SVM dataset are such that this quantity is always greater than equal to 1. So now this quantity is always positive. And now we want to find alpha I for which this is minimized. Then we will essentially go to an infinite value of alpha I, because as alpha I keeps increasing, this quantity becomes smaller and smaller because of the negative value, and so essentially we will reach a value of minus infinity. So here remember that we also put a constraint that our alpha i's must be greater than or equal to 0. So because of that, we minimize with respect to theta and theta naught and maximize with respect to alpha I. So what do you have to do? You have to first minimize LD with respect to theta naught and theta, and then whatever you get, you maximize with respect to alpha I, subject to the constraint that alpha I is greater than equal to 0. Okay, so now how do you do that? For minimization, of course, we use the same expression that you differentiate your LD with respect to the theta and theta naught and then equate that to 0. So now this is our expression over here. So first we take LD, differentiate that with respect to theta naught. So what will happen? This thing will go away because there is no theta naught over here. This thing will go away. This one will go away. What will remain is alpha I times yi summation. So that is what we get. So when we do dou LD by dou theta naught is equal to 0, what we get is that summation of alpha I times yi must be equal to 0, and the summation is over 1 is equal to n. Now when we want to differentiate with respect to theta, so this norm will give us theta, this will go away, this will give us simply alpha I yi times xi, and this 1 will also go away. So what we have is that when we take gradient with respect to LD and equate that to 0, what we get is that our theta is equal to summation over all I, alpha I, yi and xi. And now when you take this expression for theta and you substitute it back in this Lagrange function, what you get is what is called the Lagrange dual objective function. So now substituting these in expression for LD, what we get is that our LD is equal to summation over all I alpha I. So I'm not working out all the steps, but they are fairly simple. I expect you to do it on your own. I summation another index I prime. This index I prime is coming because you have a theta norm square over here. So this you denote as theta transpose into theta. So for one you take the variable I, for another you take the variable I prime. So here you have summation over I prime, alpha times I prime, y times I prime, and then xi transpose times xi prime. So this is now the Lagrange dual objective function. And now your objective is to maximize this LD over alpha I. So find alpha I such that this Lagrange dual objective function is maximized. And what can be shown is that this Lagrange dual objective function is concave. So the Lagrange function or the Lagrange primal function which we had earlier, this one was convex, and that's why convex with respect to the parameters theta and theta naught, and that's why it has a unique minima. And this Lagrange dual objective function is concave with respect to its parameters alpha I, and that's why when we maximize this we find a unique value for our maximum of LD. And this can be solved using quadratic programming. We are not going to go into the details, but those who are interested are of course welcome to look it up on their own. So this essentially is what support vector machines is all about. But here there is one more condition which is called the Karush-Kuhn-Tucker condition, and which says is that your parameters alpha i's are non-zero only for the points which are located on the margin. Okay, so that is an important criteria that you must remember, that your alpha I is non-zero only for the points on the margin. So what are the points on the margin? The points on the margin are the ones which are lying on this dashed lines, which are the closest to the decision boundary. And these points which are on the boundaries, these are called the support vectors. And this is why this algorithm is called the support vector machine, because the whole objective of this algorithm is to find the support vectors which are closest to your decision boundary and then try to maximize their distance from the decision boundary. So the alpha I parameters that we have, they are non-zero only for these support vectors which lie on the margin. For all other points, these values of alpha I are exactly equal to 0. So essentially your expression summation I alpha I yi xi, which determines your model parameters theta, is only governed by the alpha i's for the support vectors, because all other alpha i's are exactly equal to 0. And here note that alpha I and yi are scalars, but xi is a vector, because of which your theta is also a vector. So the dimension of theta is exactly equal to the dimension of xi. So now what SVM does is that it maximizes this function with respect to alpha I by the use of quadratic programming. So as I said, those who are interested are welcome to look it up on their own. But most importantly, take a look at the Python code which is there in the description box, and write a program to implement it on their own, because that is the only way by which you can deepen your understanding of this very important subject. So once again, to emphasize and to repeat the most crucial difference between logistic regression and support vector machines. In the case of logistic regression, we find a linear decision boundary, but also try to estimate the probability of our classification, which makes it difficult to handle outliers because it distorts the logit function. In the case of SVM, we completely do away with this probability estimation and only find a decision boundary. Okay, so here we are not talking about the probability of classification of a point, but only whether it is classified as +1 or -1. So that is a loss that SVM has to suffer. But what do you gain? You gain, of course, the ability to handle outliers, but you also gain the ability to handle much more complex nonlinear decision boundaries. So in logistic regression also some amount of nonlinearity can be handled, especially if you know how to transform your variables so that in the new space you can have a linear decision boundary. But in SVM, you have a lot more flexibility and ability to handle arbitrarily complex nonlinear decision boundaries. So how that is done, we will see in the next video. Till then, stay connected.